Hello everyone. Today I want to talk a little bit about the equations used for distance, speed, acceleration, and time. When I'm tutoring students that a lot of them mix up these equations and use the wrong units and have many misconceptions about it. So let's do a simple problem involving these kinds of variables, and I can explain many pitfalls that students have and how you can avoid them. So you might use different variables depending on what class you're taking, but in general, we can say that d equals d naught plus v naught t plus 1/2 a t squared. So d represents distance, v is velocity, a is acceleration, and t is time. So d naught represents initial distance, and this is initial velocity. And you might use the same equation but with different variables, and depending on what education level you are currently at, you might be given a formula with this. Otherwise, you can derive this equation using integration, but I won't be covering that because it's not in the scope of what I want to show. So many students, well, you have to interpret the problem correctly and make correct assumptions. It's not just that. Sometimes you might have a problem that involves many kinds of variables and many different kinds of units. When you're using this equation, you just have to make sure the units cancel out. So when you're adding units, you have to add the same kind of units. So let's say you have meters. That means you can only add meters. You won't be able to add meters per second to meter, so you have to make sure that when you're multiplying and dividing, the units cancel out correctly, and that you're able to add these units up. For example, let's say we have meters. That means velocity would probably be in meters per second. Time is in seconds. Seconds cancels out, and you get meters. Same with the acceleration. Acceleration would be meters per second squared. What that means is that each second you're gaining a meter per second, and time is second squared. They cancel out to get meters, so you're just adding meters together, and in the end, you'll get your distance as meters. Now, you might not be using these exact units, but as long as you just make sure they cancel out and that they're consistent with each other, like seconds, seconds, meter, meter, as long as they're consistent, it'll work out for you. So let's do a simple problem. Let's say that an officer has to catch a robber. Okay, let's say that this is the cop and this is the robber. Whoops. And let's say that the robber is 100 kilometers away. So that's the distance between them. And let's say that they're both traveling in cars on a highway and that the highway is perfectly straight and they're just going straight on the highway. Let's say that the robber is slow and the robber goes constantly at 20 kilometers per hour. So these are SI units, so maybe if you're in the US, you might be using miles per hour, so you can always convert back and forth. What units you're given, it really depends on what country you're living in. Maybe you'll be given different kinds of problems depending on which country you are in. Although, like, most of the countries will actually use SI units, with the exception of the United States. So, the rubber constantly goes at this speed, starting at this point. The officer goes at, let's say, 50 kilometers per hour. He's speeding because he knows, oh, there's a fugitive and you have to go fast. And not just that, he's accelerating, but his car is kind of slow. It's accelerating at a rate of 10 kilometers per hour squared. So physically, that would mean he's accelerating 10 kilometers an hour each hour. That's what the square really means. So when you see this kind of problem, and you'll be given it in word form, and you have to kind of do this yourself, but you might sometimes have to make equations to represent these conditions, and you'll have to solve it. And again, we'll just use the equations we have up here, and then you kind of have to make a set of coordinates yourself. You have to decide what's positive direction, what's negative direction, and we go from there. So for the robber, let's just say the distance of the robber, it can be represented by 100. But let's say we want to use meters instead. But it doesn't matter because it'll all cancel out in the end if you keep using kilometers, but let's just use meters. Usually I prefer using just those SI units, and in most equations you'll have to use meters. This isn't an empirical equation. This isn't like a line of best fit or anything like that. There's no correlation or anything, so you're free to use whatever units you want, but for consistency's sake I like to convert it to meters, and we do that by multiplying by 1,000. So that's the initial distance, 100 kilometers away. Let's say that this point is 0, and it's 20 kilometers, it's its initial speed, and since that's kilometers, I'll multiply by 1,000 again, and we multiply that by the time, and there's no acceleration. Cop. So now the cop is at, in this little coordinate graph that we made, it'll be at 0 initial distance. And we just repeat the same process. And if you're wondering why the half is there, it's just from the integration when you actually do the math. So just, if you're not sure where the equation comes from, if you're at that education level where you don't know where it comes from, don't worry about it. Most likely you'll be given a formula sheet to use. So the acceleration is 10 per hour, okay. And I'll multiply that by 1,000 t squared. Okay. Let's make this a bit easier on the eyes. Yeah, watch out, because yeah, these are pluses and these are t's. But if you simplify, you should be able to get these equations. And we want to see how long it takes the officer to catch up to the robber. So all we have to do is just set the distances to be equal to each other. So that means that okay, and you'll see that there are nonlinear parts of the equation because of the t squared, so that means that you won't be able to use, you know, like this is actually a system of equations, but it's a nonlinear system because of this squared here, so that means you won't be able to use matrices to solve this, but that's okay, because it's just a simple parabola problem. You can just factor the equation and get the roots, because you'll get 2 roots because the highest order is 2. Well, you'll get up to 2 roots, it really depends on how the numbers work out. So we simplify this, just move everything to one side. No, it's this. Yeah, and then you can factor it, or if you have a calculator or a computer or anything, most will have built-in quadratic equation formulas, or you can substitute it into the quadratic equation yourself, and you'll see that you'll actually get 2 roots. You'll see that t equals, so we'll get 2.385, and t equals negative 8.385, and these units will actually be in hours. So yeah, if you wanted, you could have converted the hours to seconds as well, but in the end, when they're all consistent, they'll cancel out in this particular equation. So these will be both in hours. And you know, I made this problem up on the spot. It's not the most realistic problem. We make a lot of silly assumptions, and the magnitudes are not really that good, and you know that it's not really realistic. Like, you can be accelerating at a non-constant rate and a whole bunch of complications. There could be curvature in the highway instead of it being a straight line, but it's just a fun little problem. But let's finish it. So one is negative and one is positive. So in a physical problem like this, you ignore the negative answer, and you know that, oh, it'll take him about 2.3 hours, and it makes sense. It's not the most precise problem, but it's not something like a billion hours, and it's not something like 2 seconds. So you'll see that it makes sense, given that, oh, it's 100 kilometers away. I mean, yeah, that's fair enough. So the key to solving this kind of problem is that just make your assumptions reasonable, be very careful with your units, make sure you have the equation correct, and when you make these equations, you can write down all the units and make sure that they cancel out correctly. And then you solve for it, and you see which answer makes the most sense. And in an easy physical problem like this, you can see that the positive answer is the correct one. That might not always be the case if you're dealing with something that could have a negative solution, then that might also be correct. You might have to see what answer suits the scope, is the solution to the problem that you're setting up. Sometimes you might have to plug it back in and see what other variables change as well as a result of this. So yeah, this is just a simple distance time problem. It's very commonly done in younger high school grades, but there's a lot of elegance to it. I hope this video helped you out. If you found it useful, please give it a thumbs up. Please also consider subscribing to my channel so that you can receive all of the latest videos first.